This is Big Brother Engineering, and welcome to this presentation on RANS turbulence models in CFD, where I'm going to use different RANS turbulence models to predict stall on a NACA 4412 aerofoil. So just as a reminder, here are the Navier-Stokes equations, and these are the equations that govern the motion of 3D incompressible flow. Okay, it would be nice if we could solve these equations and figure out what the velocity components were to figure out what our flow looks like, but these equations are actually very hard to solve due to the fact that we have non-linear terms in the equation. So we're squaring non-linear unknown terms, which makes them non-linear partial differential equations, which have been shown to be quite difficult to solve. So typically different approaches are used to solve the Navier-Stokes equations because they're very difficult to solve. Just an introduction to turbulence and fluctuations as well before I introduce the RANS equations. So turbulence is quite random and very hard to predict, but if we have a look at how turbulent quantities vary over time, we can generally determine a mean quantity. So if we look at the x velocity here, it fluctuates quite randomly over time, but we can determine a mean component, and then we can decompose the velocity at any time into a mean component plus a fluctuating component. And the purpose of doing this decomposition is to determine the effect of turbulent fluctuations on the mean flow. Okay, so we want to solve for the mean flow quantities rather than the velocity at every single location in time, and that will make solving the equations a little bit easier to solve using a RANS approach. So using this decomposition of decomposing turbulent quantities into a mean component and a fluctuating component, we sub it in. I'm not going to go through the derivation here, but we obtain the RANS equations then, the Reynolds-averaged Navier-Stokes equations. And in doing this decomposition into mean and fluctuating components, we introduce these extra unknown terms. So even though there's 9 terms here, this is actually 6 unknowns that we need to solve for. And that's the so the reason that is because our cross terms are actually equal here. So if you count this up, we have 6 unknown terms here, and these are generally called the Reynolds stresses, and they're usually written like this with this notation here in suffix notation. So if we can solve for these Reynolds stress terms, then we can solve the RANS equations and determine our mean flow quantities, which is what we want. So to solve for the Reynolds stresses, typically a Boussinesq hypothesis is used, and the Boussinesq hypothesis draws an analogy between the viscous laminar stresses and the turbulent stresses. So you may have learned from your brief from your fluid mechanics, very first fluid mechanics course, that the shear stresses in a laminar flow are related by the velocity gradients and the dynamic viscosity here. This only holds for laminar flow, but what Boussinesq hypothesized was that, okay, maybe for turbulent flow we can propose this eddy viscosity or turbulent eddy viscosity, which also relates to the velocity gradients, which would give us our turbulent stresses. And if that were true, and if we could solve for this turbulent viscosity, we could then solve for each of the Reynolds stresses. So in suffix notation, here is how we would write the Boussinesq hypothesis. This extra term here is just to include for normal stress terms, we have to add this 2/3 rho k at the end. But as an example, the tau xy term would look something like this here if we were to use this eddy viscosity approach to solve for the Reynolds stresses. So all we need to know then is this eddy viscosity, and we can solve for each Reynolds stress term, sub that back into the RANS equations, and then we can solve for our mean quantities. So we then need a model for mu of t. So you can start to see how all these models and approximations are coming into CFD, where we're taking the RANS, or we're taking the Navier-Stokes equations, we're then reducing it to the RANS equations, we're then making an approximation for the Reynolds stresses, and then we're modeling the eddy viscosity to find them in Reynolds stresses. So all these approximations are just starting to build up, But nonetheless, how do we model mu of t to solve our equations? The most simple model is the mixing link model, because this takes no extra transport equations to be solved. I'll explain what that is shortly. And then some more general approach, the most commonly used approach that you might see in a software such as ANSYS would be K epsilon model, the K omega model, or the K omega SST model. And I'll go through each of these models in detail shortly. But first, the mixing link model, the most simple model for the eddy viscosity. So as a reminder, the kinematic viscosity is the dynamic viscosity divided by the density. So in a similar manner, the turbulent kinematic viscosity is the eddy viscosity or eddy turbulent viscosity divided by the density. We can determine the kinematic turbulent viscosity by using dimensional analysis. Since the units of the kinematic viscosity are meters squared per second, we can say that the turbulent kinematic viscosity should be a constant times a velocity scale times a length scale. And in a 2D flow where tau xy is the major Reynolds stress and the major velocity gradient is du dy, we can also approximate this velocity scale as a constant times du dy times L. Combining this into this equation here, we obtain a final expression for the turbulent kinematic viscosity as a mixing length, where I've combined both constants into this mixing length term, squared times the magnitude of du dy times du dy. This is a very simple model for the kinematic viscosity in terms of an algebraic expression. So some problems with the mixing link model is it doesn't tell us how turbulence quantities are created and destroyed throughout the flow. It's a very simple algebraic model for the kinematic viscosity that just varies with a length scale, so it's an algebraic expression. And it doesn't tell us how turbulence is convected and diffused throughout the flow. So how turbulence moves throughout the flow. It's convected, diffused, created and destroyed all throughout the flow as the flow moves. So that's a problem, because we can't really solve for some very complex 3D flows as we would like to. It's only very valid for 2D canonical cases. So in order to figure out how turbulence changes as it moves through the flow, we have to solve what's called a transport equation, and that's what's typically done with the K epsilon model, as I'll show now. So the K epsilon model solves two transport equations, one for K and one for epsilon. K is the turbulent kinetic energy and epsilon is the eddy dissipation rate. So what these quantities are is telling me how the turbulent kinetic energy changes throughout the flow and how the turbulence is then dissipated via eddies throughout the flow. So just these relations here I've put in the screen to show at the end of the day what we really are trying to do is solve for the eddy viscosity. But if I can solve a transport equation for K and epsilon, I can figure out how turbulent quantities change throughout the flow and then use that to solve for my eddy viscosity and solve for my RANS equations. So the velocity is related to the velocity scale, I should say, is related to the turbulent kinetic energy via the square root of the kinetic energy, and then also the length scale, similar to what we had in the mixing link model, is related to the length scale by k to the 3/2 divided by epsilon. So the transport equation for k and epsilon, what does that look like? Well, this is what it looks like, and it can be quite daunting if you haven't a background in vector calculus. But all these two equations are saying is this first equation here is the transport equation for k, and the bottom one is the transport equation for epsilon. And as I said already, we just want to determine how turbulent quantities change throughout the flow, how they're convected, diffused, created, and destroyed. The first term here is how the kinetic energy changes with time. This term is our convection term, our diffusion term, our production term, and our destruction term. And the same here for each term is in the same position here for epsilon. So what this then tells us is how k and epsilon change as it moves through the flow, and this is important because it's a step up from the mixing link model. We can now use this to model some more 3D cases, some more complicated cases. So some problems with the K epsilon model. This was one of the first turbulence models used in CFD, proposed by Launder and Spaulding in 1974. It has many advantages in terms of the fact that it's so well established for many canonical flows, so for any canonical 3D flows. It's very robust, economic, and it's reasonably accurate, but some challenges have came up over the years. Some of these challenges are the fact that it embeds in it this assumption of isotropic turbulence, and this is basically that it's assuming that all turbulence quantities are the same in all directions. So in X, Y, and Z, all turbulence quantities are fluctuating up, down, the same amount in each direction, which isn't always true for all types of flows. It also doesn't capture the sensitivity of turbulence to secondary shear strain terms, and what this basically means is there's a very classical problem that the K epsilon model has in predicting round jet separation rate, or the spreading rate, sorry, I should say. It also requires nonlinear damping functions to model the wall behavior and behaves very poorly in the presence of an adverse pressure gradient. This is important, and we'll see this when I do an example of an airfoil in ANSYS. So to overcome the problems of the K epsilon model in terms of the wall modeling, the K omega model was proposed, and this solves two transport equations, one for K and one for omega, where omega is the turbulent frequency, which is simply epsilon divided by K. And this is, again, it's a similar approach insofar as we're solving two transport equations for two turbulent quantities, but the major difference with the K omega model is that this can be integrated to the wall, as I said. What this means is that this behaves a lot better near walls. It can model the viscous sublayer a lot better, and it behaves better in the presence of an adverse pressure gradient, which is what we have at the top surface of an airfoil. So this was developed to help with the predicting separation over an airfoil over the K epsilon model. Here's the transport equations for K and omega. Again, quite similar. All transport equations take the same sort of form. So how quantities change with time, how they're convected and diffused, created and destroyed in the flow. If we can solve these two transport equations for K and omega, we can then sub that back into this expression here for eddy viscosity, and we can then solve the RANS equations. So some problems and some advantages with the K omega model. So again, this can be integrated to the wall without damping functions. I haven't mentioned that, but the K epsilon model really has trouble being integrated down to the wall, which means it has to use these damping functions to model the viscous sublayer properly, and this has been shown to be quite poor in modeling separation over airfoils, etc., which was why this model was developed in the first place. So the main advantage of this model is it can be integrated to the wall without the use of these damping functions. So this gives it much better performance in adverse pressure gradients, and much better performance from mixing layers and free shear layers. So some challenges with this is that it embeds in it again the assumption of isotropic turbulence, and also what's been shown with this model is that it's very sensitive to free stream values of K and omega. What this means is at the very start of the simulation that you might do in a software such as ANSYS, you specify turbulence intensity at the inlet, and this model is quite sensitive to what values you provide for K and omega, or in general just the turbulence at the inlet, and that's kind of an issue because it's very difficult to determine what the turbulence intensity is at the inlet in the first place. So the results are actually very, very sensitive to what you provide at the inlet, which is quite a problem for this model. So to overcome the problems encountered with the K omega model, the K omega SST model was proposed, and what this does is it uses the K epsilon model in the free stream and the K omega model at the wall, and this is advantageous because it uses the benefits of both in the one model, and it uses then a blending function to blend between the two. So it uses the K epsilon model in the free stream where the K epsilon model was shown to behave quite well and the K omega model was quite poor, and then it uses the K omega model near the wall to help predict with this adverse pressure gradient and wall behavior that the K epsilon models behaved quite poorly with. And this model is quite suitable for aerodynamics applications and it's one of the most popular models for aerofoils. So advantages with this model is it has superior performance for aerofoils without a dependency on the free stream values. But some challenges is that it does tend to overpredict levels of turbulence in areas with normal strain, such as stagnation points. So just like any model, you have your advantages and your challenges. So I conducted a study in ANSYS of a NACA 4412 airfoil using the K epsilon model, the K omega model, and the K omega SST model. NACA 4412 is a very basic asymmetric airfoil. I studied all three turbulence models over a variety of angles of attack, so all the angles of attack shown here. It was 21 cases in total. The Reynolds number was 3 million, and I had a Y plus value of less than 1, so that means basically I had quite a fine mesh around my airfoil to properly model the viscous sublayers. And what I wanted to do was to compare these different turbulence models with each other and see which model could best predict the stall on the airfoil. Before running any simulation, it's always a good idea to have a look at the expected results of what we would expect from the simulation. So I have a reference here of Abbott et al. Of a NACA report 824 where they determined the lift coefficient versus angle of attack for NACA 4412, and the circles here represent our Reynolds number of 3 million. It's quite hard to see here, but I've taken the values and put it in the table here of the angles of attack and the lift coefficient they determined from the experiment. Looking at this, we would expect the stall angle of the airfoil, so in other words the maximum lift coefficient, to be 14 degrees, looking here, and that lift coefficient was 1.5. So after I first ran the study, again, here's another good check, I suppose, is you should always take a look at some very basic flow parameters before continuing on into a big case study using CFD. So what I mean by that is, before I ran all 21 of these case studies, I took this first model here, I had a look at the flow field, and I made sure all the parameters were behaving as I would expected, and that the flow field was behaving as expected. And the K epsilon model at 10 degrees, so the flow was coming in here at an angle of 10 degrees. I have a stagnation point in front of the airfoil. I have a very low velocity region here, which looks like I'm properly modeled the viscous sublayer. I have a high pressure region below the airfoil and a low pressure region above the airfoil, which means the airfoil is behaving as expected, and I can then move on and study the K epsilon model over a wide range of angles of attack. Now I know the flow field is behaving as I would expect it to for 10 degrees. So running these three turbulence models over a bunch of different cases, we have the K epsilon model here, the K omega model here, and the K omega SST model here, over a wide variety of angle of attacks. Let's look at the data. So before looking at the table, I think the graph is a little bit more intuitive. We have angle of attack on the bottom here and lift coefficient on the Y. Here's the experimental data here, so it clearly shows the stall angle here, or in other words the maximum lift coefficient at 14 degrees, and then slowly decreases. Secondly, looking at the K omega SST model, it looks like we had stall at about 15 degrees here, so the maximum lift was at about 15 degrees here before it then decreased. So experimental value was 14 degrees for the stall angle, and the K omega SST was 15 degrees. Taking a look then at the K epsilon model, it looks like it stalled here at about 18 degrees, so that's where the maximum lift was recorded, which is again 4 degrees off 14 degrees here, and then the K omega model was all the way up at 20 degrees here, so quite far off. So taking a look at what values were actually recorded for the stall angle, the K epsilon model showed a coefficient lift of 1.79 as the maximum value recorded. The K omega model showed 1.97, and the K omega SST model showed 1.75. So this is all approximately 20 to 30% difference to what was recorded in the experiment. Okay, taking a look at then the flow field. So in the experiment, 1.5 was recorded as the maximum lift, and it stalled at about 14 degrees. But the K epsilon model, the lift coefficient kept increasing, until it stalled at about 1.79. So I took a look at 16, 18 and 20 degrees here just to have a look at what the flow field is doing. And at 16 degrees here, which is 2 degrees past the point where we would expect stall to occur, we can see that the flow is just about starting to kind of recirculate there. This streamline here looks like it wants to kind of turn around and start rotating due to the adverse pressure gradient, but it hasn't stalled quite yet. Then at 18 degrees we do start to see recirculation on the airfoil, and we do record the maximum coefficient of lift, which represents the stall of the airfoil. And then finally at 20 degrees, as we would expect, if you keep increasing the angle of attack past the stall angle, you get major recirculation at the top surface of the airfoil. Doing the same for the K omega model, so taking a look at the flow field. At 16 degrees, we see this sort of not quite stalling yet, but wants to separate from the airfoil. And we have a much higher coefficient of lift as compared to the K epsilon model. And then in the next picture here, so 18 degrees, we have the 1.96 coefficient of lift and an angle of attack of 18 degrees. But strangely enough then, going to 20 degrees, the lift coefficient actually increases just a slight bit more, up to 1.97. Which is what I predicted the stall angle to be, where I defined the stall angle as being the maximum recorded coefficient of lift. And then the K omega SST model, again, the stall angle was recorded at 15 degrees, but I just thought it would show what the flow field looks like at 16, 18 and 20 degrees, and it's behaving as expected with what we would expect the experiment to behave as. So the experiment stalled at 14, and we would expect the flow to start recirculating at the top part of the airfoil and keep doing so as we increase the angle of attack here. And the K omega SST clearly shows this behavior where at 15 degrees it had stalled, and then at 16, 18 and 20 we have increasing amounts of separation. So comparing all three results here, we can clearly see that the K omega SST model predicted a stall angle closest to the experiment, where the experiment was 14 degrees. We predicted about 15 degrees for the K omega SST model as the stall angle, whereas the K omega and the K epsilon model predicted 18 and between 18 and 20 degrees. So the K omega SST model seemed to closely predict the stall angle of the airfoil, and also we can see that at 16 degrees it's the only model here that predicts a lot of recirculation at the top part of the airfoil, whereas the K omega and K epsilon model don't. So a conclusion on this study then, we can clearly say that the K omega SST model best predicts the separation angle of the airfoil. The K omega model though is actually quite poor at predicting the separation of an airfoil in this example. This is not what we would expect from the theory, as it's been shown in the literature that the K omega model is quite good at predicting separation on an airfoil, but it's just very sensitive to inlet turbulence quantities. And I kept the turbulence viscosity ratio at 1 for all three models. Had I have changed this and maybe done a sensitivity study on the turbulence viscosity ratio, I would expect the K omega model to, over a broad range of studies, behave better at predicting the separation of an airfoil, because inherently the K omega model itself was actually created to tackle the problem of the K epsilon model with predicting separation and adverse pressure gradients. So again, it just wasn't the scope of this study, but I would expect the K omega model to behave better after conducting multiple different studies of turbulence viscosity at the inlet and looking at the results. The K omega model also behaves quite poorly in the presence of an adverse pressure gradient. So both the K omega and K epsilon model predicted stall angles of 18 degrees. K omega predicted 18 to 20 degrees, which is quite far off the experiment. So the main conclusion is that the K omega SST is generally preferred for airfoil simulation, and I would recommend reading the ANSYS theory guide before using this model in your own simulations. But what about other turbulence models? So there is some other turbulence models that can be used in software such as ANSYS that I haven't talked about, and one is the Spallert-Almaraz models. This is a one equation model, so what that means is only one extra transport equation has to be solved rather than two, such as the K omega and K epsilon models that I had shown. And this is quite good for turbomachinery applications where the flow is in an adverse pressure gradient, but it's wall bounded, so there's no separation. Also, there's a Reynolds stress model, and this is good for predicting anisotropic turbulence. So, as I've said during the talk, is that there is an assumption in all these models that there's isotropic turbulence behavior, so that the turbulence quantities fluctuate the same amount in each direction. That's not true for all flows, such as swirling flows in a swirling combustor, for example, where you might have more turbulence in the x direction rather than the y and the z directions. To properly model this, it's recommended to use a Reynolds stress model where an Eddy viscosity model actually isn't used. It models the Reynolds stresses directly using 6 transport equations for each Reynolds stress and 1 equation for epsilon. And this is recommended for anisotropic flows. But again, you have to solve 7 transport equations, so that is a lot more computationally demanding than a 1 equation or a 2 equation model. Okay, so in summary, the K epsilon model is one of the most validated models for a canonical flow. It does have some problems, however, with large secondary shear strains, and a classic problem of the K epsilon model is that it has trouble predicting a round jet spreading rate. There are some variants of the K epsilon model that can help tackle this, such as the RNG and realizable. Also, for flows with adverse pressure gradients, the K omega model is typically recommended, with the SST variant being one of the most well established for an airfoil example. So, some references then. I'd highly recommend a book by Versteeg, which I used as a source for many of my images in this talk. An Introduction to Computational Fluid Dynamics. It's a great book. I'd highly recommend it. I'd also highly recommend a YouTube channel called Fluid Mechanics 101. His YouTube videos really help drill the ideas into your head after you read about them. And for these notes and for the ANSYS files, if you'd like to gain access to them, just send me an email at brigbutterengineer@gmail.com.